Hi guys, welcome back. It's Mrs. Webb here, and today we're going to continue on with our 2D vector diagrams, except this time, instead of doing a scale diagram like we were doing last time we chatted, we're going to talk about doing calculations. And first and foremost, because everyone always asks, I just want to make very clear that there are different ways to solve these 2D vector problems. But in terms of Alberta Physics 20 curriculum, the method that you need to demonstrate an understanding for is the component method. And so we're going to be using this vector component method moving forward from now until the end of the kinematics unit, and then we will see it again when we get to the dynamics unit. So you need to be competent and comfortable at solving these problems quickly and efficiently. Now remember that a scale diagram does the exact same thing, and so sometimes you might find on an exam that in a long answer problem, if you're running low on time, sometimes it might be to your benefit to do a scale diagram to get the answer, and you would get your full points and all of that just doing a scale diagram versus doing the component method. But you need to know how to do both, right? And you need to be quick and efficient with both. So in order to use vector components, the first thing that you guys need to be comfortable with is basic trigonometry. And the basic trig that we're going to use is we're going to need to be able to calculate angles of a triangle. So you have to remember your SOHCAHTOA. And remember that SOHCAHTOA is always with respect to the angle that is being measured. And so I've got my sign here. So is opposite over hypotenuse. And in this case, here is my angle, right? This is the angle. So with respect to this angle that's being measured, this is the opposite side. And then the hypotenuse is the longest side of the triangle. With respect to the angle I've drawn here, this is the adjacent. Adjacent is just another way of saying beside the angle, and then over the hypotenuse. And then tangent is the opposite over the adjacent. Okay, so that's your basic SOHCAHTOA. The only other basic trig thing that you need to know is Pythagorean Theorem. And so that is your hypotenuse, c squared, is equal to your side a squared plus your side b squared for a right triangle. So those four things you have to remember, and that's pretty much all you need to know in terms of math in order to solve these vector component problems. Now, thing to remember with any of the vector diagrams that we have been doing so far is that the sum of all of those vectors that we were doing when we were doing 1D motion or when we were drawing scale diagrams for 2D motion, the sum of all those vectors gives you the resultant vector. Okay. And that's kind of the general rule. The sum of all of your vectors gives you the resultant diagram. So if I were to break my vector, this black vector, if I were to break this into its x and y components, the sum of the x and the y components gives me the resultant vector, right? And the x and the y components, when you draw them, they have to start, right? If this is the resultant vector always goes from the beginning and points to where we finish. And we use the tip to tail method. That means that the x is going to have to extend toward the right, and then the y is going to have to extend up toward the north so that the tip of the y meets the tip of the resultant vector. Okay. So that's kind of the first thing. Now, when we're doing several vectors, we're going to break each of those vectors into the x and y components, and the sum of those x and y components is going to give me the x component and the y component for the resultant vector. So I'm going to give you some examples because I know that that is a very, very wordy explanation, and I probably lost a good chunk of you guys, several sentences ago. So I'm going to give you a nice, easy example here to start, where our particular student is just moving up or across. So the student drives his car 6 kilometers north before heading 6 kilometers east, and finally 2 kilometers north. And we want to find what is his overall displacement, right? So this is a 2D problem. We need our Rosetta. for all of these problems, you'll always say north is positive, east is positive. My preference is that you always put a little rosetta here just to orient yourself for each of your vectors. And this will become even more important when we get to the vectors that don't go up and down and left to right, right? And that'll be the next example here. So put your little rosetta here. This is the start. We travel 6 kilometers due north, and I've made my, arrow represented, the length of my arrow representative of that 6 kilometers. Then we travel 6 kilometers due east, and I've made this arrow representative of 6. And then I travel 2 kilometers north, and I've made my arrow representative of 2 kilometers. So I don't have to do a scale diagram, but I should make those arrows representative. The better I draw my vector diagram, the easier my calculations will be. And so what that tells me is that my resultant vector starts here at the beginning, at the origin, and it points to where we finish. And so that tells me that when everything is said and done, but if I've drawn this diagram correctly and then look at the size of this arrow, I'm pretty sure that my magnitude, my displacement should be larger than 6 kilometers, right? Because if I've drawn everything in terms of an appropriate length for each of the arrows, this is my 6 kilometer arrow, and this is quite a bit longer. So I'm anticipating something larger than 6 kilometers, and I'm anticipating something that will be in this northeastern quadrant, right? Because I've got my little rosetta here. So that's kind of what I already know my final answer should be. So first thing we do with all of these component questions, we're always going to list our x and our y. And then here in the left margin, I'm going to put the vectors. So I've got my A vector, B vector, and C vector. And I've labeled, this one A, B, and C. And I always draw the vector so that I can kind of keep myself oriented. This is heading, due north, which means it is right on top of the y-axis. And if it's right on top of the y-axis, what that tells me is that there is no x component to this vector, because this vector is sitting on top of that y-axis, which means it has a 0x. So I'm going to put down 0 kilometers for x and 6 kilometers for y. And my arrow is pointing due north, which is positive. So I'm inserting my positive sign there. My B is pointing due east, which means it's lying on top of the x-axis. And if it's lying on top of the x-axis, then that means it does not have a y component. So I inserted 0 kilometers for the y, and I'm saying that it's 6 kilometers east, which is a positive for the x. And then my last vector is C, which points due north again. Again, it's sitting right on top of the y-axis, so it's got a 0 kilometer x component. And the y component is 2 kilometers. My vector points due north, which means it's positive 2 kilometers. So those are the components of each of those individual vectors. Now the sum of each of these vectors, gives me that red resultant vector. And the sum of each of these x and y components will give me the x component and the y component of the resultant vector. So if I sum up all of my x's, I get 6 kilometers positive. If I sum up all of my, if I sum up all my x, I get 6 kilometers positive. If I sum up all my y magnitudes, I get positive 8 kilometers. And so that tells me that the positive tells me that my resultant x vector should be pointing east, and it is. And my resultant y vector is pointing due north, which is positive as well. So everything verifies that this resultant vector from my original diagram is probably drawn correctly, because these some of the x and some of the y, they match my diagram, right? So I go tip to tail from the start, I head east, then I go north, and that ends at the finish right here. And that's where my red arrow is pointing. Now what I've got here is a regular Pythagorean problem. So I'm looking for the hypotenuse, the magnitude of this resultant vector, and I've got the x and the y. So I set up the Pythagorean theorem. I rearrange and I plug my numbers in. I solve for displacement and I get 10 kilometers. And this verifies what I was thinking at the beginning, that my displacement should be larger than that 6 kilometers, right? So 10 kilometers is definitely within that range that I was anticipating. Next thing I got to do is I've got to solve for my angle. And truthfully, because I have the length of this side of my triangle, and I have the length of this side, and I have the length of this side, I could use SOHCAHTOA or TOA. I've chosen to use tan. So I set up my tan theta. Here's my angle, right? My angle is sandwiched between the x-axis and the hypotenuse. So the opposite is y, the adjacent is x. TOA, opposite over adjacent. Plug my numbers in. I'm going to take the inverse tan, and I get 53 degrees. Okay. And if I look at how this angle has been drawn, it's 53 degrees being measured from the eastern axis toward the north. So that tells me that my displacement for the particular car is 10 kilometers at 53 degrees north of east. Okay, so that's a very basic component problem. I've got one that's just slightly more complex in that there's more stuff to take into account with this one. So we've got two friends who are on a hike. They start from camp and they make their following movements. Vector A takes them 2.65 kilometers at 140 degrees. Vector B takes them 4.77 kilometers at 252 degrees. And vector C takes them 3.18 kilometers at 332 degrees. Now, we want to figure out what's their overall displacement and what is their average velocity if the hike took them 2 hours. So I'm going to draw a vector diagram first and foremost. That's always your starting point. I've got my Rosetta here, north and east are positive. I'm starting right here and I displace myself, what did I say, 2.65 kilometers at 140 degrees. Now, I'm measuring my zero from the east here. So I'm drawing 140 degrees over here. That means that with respect to my y-axis, I'm going to have an angle of 50 degrees. Then from there, we move 4.77 kilometers, and it's 232 degrees, right, if my zero starts here at the east. And that means that this teeny little angle in here that I'm referencing is 18 degrees. Then from there, my vector C, we travel 3.18 kilometers at 332 degrees. So I start my zero here at the positive x-axis and move around all the way to there, 332, which means that the remainder here is 28 degrees. And if I've drawn everything correctly, my resultant vector is going to point in this southwesterly direction. And if I look at the magnitude of this arrow, I'm thinking it's probably, between 3 and 4 kilometers is roughly what I'm anticipating, because it's somewhere between this arrow and this arrow, right? So somewhere between 3 and 4 kilometers, and I'm anticipating that it's in that southwest. I don't think, if you look at how far this red arrow has moved off of that south axis, I don't think the angle is going to be very, very large at all. So that's kind of what I'm already thinking before I even start calculating. Now I'm going to move to the calculations. And so I set up my X and I set up my Y. I've got my ABC vectors. I'm drawing my A vector. And remember, I referenced my angle here. I referenced it up here with the y-axis. So I'm going to start at the beginning, at the tail. I'll draw my y up, and then I have to send my x to the left in order to meet the tip of the A vector. Okay? Because remember that this A vector is going to be the sum of the x with the y. And so in order to solve for the magnitude of this x vector, it's opposite my 50 degrees, and I have the magnitude of A, which is the hypotenuse. So this is sine, opposite over hypotenuse. And so I'm going to take 2.65 kilometers times sine 50, and that gives me 2.0300177 kilometers. Hold on to all the numbers. Notice that my x component has to point west, which means that west, I said, was negative based on my Rosetta. So I need to insert a negative sign here. My y, with respect to the 50-degree angle that I had measured, I had referenced, my y is adjacent. And I have the hypotenuse, A, so that's 2.65 kilometers times cos 50. And I got 1.7033871 kilometers. My y, if we look at my diagram, is pointing due north, and I said north is positive, so I insert a positive sign there. Now I'm going to do the same thing with B and C. B, I had drawn like this, pointing down, and I had referenced that 18-degree angle. So if this is the start, the tail is always the start. I need to get to the finish. So I'm going to draw a vector pointing due south. That's my y-axis. And then I have to draw a vector pointing due west in order to get to the finish. And that's my x. So that tells me that the x is opposite my 18-degree reference angle. And I've got the magnitude of b, that's my 4.77 kilometers. So I'm going to solve for x, which means I take 4.77 kilometers times sine 18, and I got 1.474011 kilometers. Because x is pointing due west, I have to give it a negative sign. So I insert my negative. Now I'm going to do the same thing for y, and y is adjacent to the 18 degrees. So that's cosine. So I take 4.77 kilometers times cos 18. That gives me 4.5365396 kilometers. Y is pointing due south, which is negative. So I insert the negative sign. And I hold on to all my digits. And then we're going to do the same thing with the C. So this is my C that I had drawn up above. I had referenced this 28 degrees. So I need to figure out, well, which way are my x and y components going to go with respect to that angle that I referenced. So I start at the beginning and I go toward the finish, which means I have to draw an x vector that points due east and then a y vector that points due south. In order to solve for the x component, it is adjacent to my 28-degree angle, and I have the magnitude of c. So I'm going to multiply 3.18 kilometers times cos 28. I'm just going to pause for just 1 second. I just want to make sure we're still recording here. Yes, perfect. I get 2.80773 kilometers, and because this x is pointing due east, I have to insert a positive sign because east is positive based on my Rosetta. Y, my y vector is opposite my 28-degree angle, so I have to use sine. I'm going to take 3.18 kilometers times sine 28 degrees, and I get 1.492196 kilometers. Notice that y has to point due south, so I have to insert a negative sign. Last, what I'm going to do is I'm going to take the sum of all of these x components, and that gives me 0, negative, including the sign. So take the sum including the signs that you inserted, and that'll give you negative 0.6962557 kilometers. And I'm going to take the sum of all the y components, which gives me negative 4.3260721 kilometers. There we go. Now, if my signs were correct in how I had drawn everything up above, these negatives here should corroborate where the location is of my resultant vector, right? So here is where I drew my resultant vector from up above. I'm going to draw that vector down here, and I'm going to measure the angle here, right, with respect to my south axis. In order to get from the starting point to the finishing point of this resultant vector, I have to draw a vector moving down and then a vector moving west, which means that my down will be negative and my west will be negative as well. So this and this sum of the x and the y must be accurate. And guys, even if I chose to take this angle, even if you chose to take the other angle, let me show you. If that's my resultant there, if you decided to go the other way, so you drew your x this way and then your y that way, and you measured this angle instead, you would notice that your components are still the same. X is still pointing due west and y is still pointing due south, right? So you're still looking at negative and negative. Right, and then the other thing too is you should if you've drawn this, more or less accurately, you should look at the magnitudes of these x and y components, and they should more or less corroborate what you've drawn here. So if I look, my x arrow is really quite short in comparison to my y arrow, and my x component, when I summed it, is really quite small in comparison to the y. So that kind of verifies everything for me. I want to figure out the magnitude of this resultant vector, so I'll use Pythagorean Theorem. Plug in all my numbers, rearrange, and I get 4.38 kilometers. Now remember at the beginning, I said when I drew this diagram, I said based on the magnitudes of each of these individual vectors, I'm kind of anticipating that this resultant vector is going to be somewhere between the b vector and the c vector. My b vector was 4.77, my c vector was 3.18, right? And so my resultant vector, I got 4.3 kilometers. I'm right within that range that I was anticipating. And then the other thing is, remember I said that I was expecting that angle to be really quite small because this vector is almost on top of that southern axis. So now I'm going to calculate that. And I chose to go with tangent again. And the tangent is the x, the opposite, over the y, the adjacent, right? So with respect to this angle, opposite over adjacent. I'm going to rearrange and plug my numbers in, and I get an angle of 9.14 degrees. Now, when we're solving SOHCAHTOA for these physics problems, you don't have to take into account the sign. You just want the magnitudes of those vectors. And what this tells me, and that's a really small angle, which verifies what I was thinking. I don't think, because I was anticipating I hadn't moved myself very far off of that southern axis. And so that tells me that the resultant vector is 4.38 kilometers at an angle of 9.14 degrees west of south. Very last thing was figure out the average velocity. So I know that I displaced myself 4.38 kilometers in 2 hours, which means that my average velocity is 2.19 kilometers per hour at, let me change this, 9.14 degrees west of south. So that's a typical x and y component vector problem. We'll give this a shot in class, but as usual, bring any questions you have with you to class. I hope you guys are doing well, and we'll chat soon. Take care.